Binomial distribution. First, we have to consider a random experiment. So, random experiment means an experiment which, even though if it is conducted many times, we cannot predict the outcome of that experiment. Such a type of experiment is called a random experiment. Now, we have to consider a random experiment which has two mutually exclusive and exhaustive outcomes. That means mutually exclusive means if one outcome comes, that will affect the other outcome. So other outcome cannot come. And exhaustion means totally only two outcomes will be there. One is called success and the other one is called failure. Okay, so for example, we can consider tossing of a coin. So either head will appear or tail will appear. So that two outcomes are mutually exclusive, because if head comes, then they at the same trial, the tail cannot occur. So if tail occurs in the one trial, then at that time, then head cannot appear. So they are mutually exclusive. And only both two outcomes are there. One is getting head, the other one is getting tail. So they are exhaustive outcomes. So suppose getting head, we take it as a success, then getting tail will be considered as failure. Okay. Then let P denote the probability of success. That is probability of getting head. Then Q is what? That is 1 minus P, which is the probability of failure. Suppose the random experiment is repeated independently n times. Let x1, x2, x3, etc., xn be random variables where xi takes the value 0 or 1 according as the outcome in the ith trial is failure or success. That means, suppose xi is the outcome of the ith trial. Okay, so the random variable which denotes the outcome of the ith trial. That value of xi will be 1 if in that trial, ith trial, head appears. Otherwise, it will take the value 0. Now, the probability of xi is equal to 0 is q, because 0 xi takes the value 0 when it fails. In failure, the outcome is failure. And so it is q, which is equal to 1 minus p. Similarly, probability of xi is equal to 1. That means the xi will take the value 1 when the success, and there is success. So it is equal to p. Now, let capital X be a random variable which is equal to x1 plus x2 plus x3, etc., xn. Then X will represent the number of success in n trials. Why? Suppose in n trials, in 3 trials we get success. Then means what? Suppose it is the first trial, second trial, third trial. Only in the first 3 trials if we get success. In the remaining trial, if that is a failure, then the value of x1 and x2 and x3 will be 1. The other x4, xy, etc., the values of other random variables will be 0. So x is equal to what? 1 plus 1 plus 1 plus other 0, 0, etc. And so the value of x will be 3. So like this only, we'll get, suppose there is 4, number of successes 5, then the value of x will be 5. So x also, if maximum or in all the n trials, success may come. Then, so maximum value of x is n. And if the not even a single time success occurs, then the value of x is equal to 0. So x assumes the value from 0 to n, 0, 1, 2, 3, etc. n. Now, P of, that is the probability of capital X is equal to small x. Small x is what the value capital U, which the capital X takes. That is given by the formula NCX P power X Q power N minus X, where small x denote the number of successes in n trials. Suppose if you put five successes there, probability of capital X is equal to 5. That is probability of getting 5 successes is equal to NC5 P power 5 Q power N minus 5. Okay. So that is the meaning. So clearly, now summation x equal to 0 to n, NCX P power X Q power N minus X. If we expand it, we'll get NC naught P power naught a Q power N plus etc. NCN P power N Q power 0. Hence, P of capital X is equal to small x, which is NCX P power X Q power N minus X, is a probability density function of a discrete random variable. Definition. Let n be any positive integer and let 0 less than p less than 1. Then q is equal to 1 minus p. Then the discrete random variable with probability density function p of x equal to NCX P power X Q power N minus X. If x equal to 0, 1 to etc. n and 0 otherwise is said to have binomial distribution, and the probability density function itself is called a binomial distribution. That means if a discrete random variable x has a probability density function like P of NCX P power X Q power N minus X, when x equal to 0, 1 to 3 etc. n 0 otherwise, then that random variable x is said to have a binomial distribution. Okay. And this PDF P of x itself is called the binomial distribution. It's theorem. Let us see the theorem. In this theorem, we are going to derive the moment generating function of a binomial distribution about the origin. And we get the result as q plus p e power t whole power n. Now, the proof is moment generating function is denoted by mx of t. Now, so mx of t is equal to x by formula, it is expectation of e power tx. So this is equal to, by expectation formula, expectation of e power tx is what? Summation e power tx into p of x. Now, instead of p of x in the next step, we have to substitute NCX P power x Q power N minus x, because we are deriving a moment generating function of a binomial distribution. And x also varies from 0 to n. Next step, this is equal to summation NCX. Now, p power of p is also x, power of e power t also x. So we can combine and write it as p e power t whole power x into q power n minus x. Now this is equal nothing but by binomial theorem, it is q plus p e power t whole power n. So the moment generating function of a binomial distribution is q plus p e power t whole power n. Okay, next theorem, addition property of binomial distribution. The statement is, if x1 tilde b n1p, that is x1 is a binomial variate with parameters n1 and p, and x2 is another binomial variate with parameters n2 and p. If they are independent random variables, then x1 plus x2 will also be a binomial variate, and its parameter will be n1 plus n2 and p. That we have to prove it now. So for that, xn, what is given, x1 and x2 are independent random variables. Then now, therefore, with parameters n1p and n2p. Therefore, mx1 of t is equal to, by the previous theorem, mx1 of t will be what? Q plus p e power t whole power n1 because the parameter for x1 is n1. And mx2 of t is equal to q plus p per t whole power n2 because the parameter of x2 is n2 and p. Then next line, now we want to find Moment generating function of x1 plus x2 of t. X1 and plus x2. So we start with x1 plus x2 of t, which is equal to, because x1 and x2 are independent random variables, by the property of moment generating function, it is mx1 of t into mx2 of t. Now we have to substitute the value of x1, mx1 of t and mx2 of t here. Then in the next step, because we can q plus p per t whole power n and q plus p per t whole power n2. So combining these two, we can write it to be q plus p per t whole power n1 plus n2. So this is in the form of a moment generating function of your binomial variate x. But instead of n here, we are having n1 plus n2. And in the place of p we are having. Therefore, we can say that x1 plus x2 is a binomial random variable whose parameters are n1 plus n2, p. So we have proved the addition property. Next, we have proved the addition property for two independent random variables. It can be extended to n independent binomial variates. That is, if x1, x2, etc., xn are independent binomial variates and with parameters ni and p, then x1 plus x2 plus etc. xn, that is the sum of the n binomial variate, will also be a binomial variate with parameters n1 plus n2 etc. nn, p. Okay. Next, we are going to derive the characteristic function of a binomial distribution, and we will get it to be q plus p e power it whole power n. So the difference between the moment generating function and the characteristic function is, it is in the same form. Only difference in that we'll have e power t. Instead of that, here in characteristic function, we are having p into e power it. So the proof is, x is, suppose x is a binomial variate with parameters n and p. Then the characteristic function phi of t is equal to, by the definition of characteristic function, it is expectation of e power itx. Now, by the definition of expectation of x, this is equal to summation e power itx ncx, that is e power itx into p of x. But here the value of p of x is ncx p power x q power n minus x, that we have to substitute it here. So in the next step, e power it x and p power x, that we can combine and write it as p e power it whole power x into q power n minus x, which is the expansion of the binomial theorem q plus p e power it whole power n. So we have derived the characteristic function of the binomial variate. Thank you.